Good morning. Welcome to the IvS seminar for today. Today we have Shreeya, who is a postdoc at Gaia at the IvS. Shreeya did her PhD between Gaia and ULB before becoming a postdoctoral researcher at the ULB in Switzerland, and then is returned to Gaia. And today Shreeya is going to talk to us about her work on VELOCE.
Can you guys hear me? Hear me well? Really well? All right, so as Rose introduced already, today I'll be talking about VELOCE, a project I was part of while I was doing my postdoc in Switzerland. This project was funded under an ERC starting grant, was based at EPFL. Currently, I am an FWO postdoc researcher here at Cepheid IvS. So before we start talking about VELOCE, I want to wake up the astronomers inside all of us. You see this beautiful time lapse of the night sky. There is one central star here, so not the brightest one, but another one here, which is not moving in this time lapse. And any guesses on which star that is? A hint, this is the northern hemisphere. Yes, Ton, go for it. So it is the, wait, with a lot of suspense. This is just not working. It's the North Pole star, Polaris. And any guesses on what kind of star Polaris is? So Polaris itself is a Cepheid, which is the kind of stars we're going to talk about, or I'm going to discuss about. Polaris itself is also a spectroscopic binary, also with a visual companion, so it's kind of a triple system, lots of funky things going on here. So these Cepheids are very interesting objects, and before we get into the details of it, I would like to walk you guys through a bit about Cepheids and what are these guys that we're going to talk about in this seminar. So classical Cepheids are going to be the focus of my talk. This is one subclass, the major class of Cepheids. These are yellow, bright supergiants. You saw already with Polaris, it's quite amongst the brightest stars in the northern hemisphere. These are bright up to 10⁵ solar luminosity. So they are so bright that you can see them even in other galaxies. You can see them even up to 30 megaparsecs if you're using HST, and even better with James Webb now. The masses of the classical Cepheid, it ranges between 4 to 20 solar masses, so you can call them low to, no, not low, intermediate mass to high mass stars. And an amazing feature about these classical Cepheids is that their brightness, it cycles over a regular period. This means they are pulsating. So these are pulsating stars. Here you have an example of datasets, which is a prototypical classical Cepheid. And you see its magnitude you're varying in a regular cycle of 5.4 days, which is the pulsation period of dataset. So over this regular pulsation cycle, the brightness varies itself as well. Which is what forms the Cepheid-PL relationship, or the period luminosity relationship. This PL relationship, or also called as Leavitt's law for Henrietta Leavitt here. I'm sorry, I couldn't find a much happier picture of her. But this is Henrietta Leavitt, who almost more than 100 years ago found this tight PL relationship for Cepheids when she was looking at classical Cepheids in the Magellanic Clouds. This is the picture 100 years ago, and if you want a more up-to-date picture, here is another example of the PL relationship in different filters with the HST from the SHOES team, which is one of the biggest teams working on the Cepheid-PL relationship. So Cepheids have they follow a very tight period luminosity relationship, pulsation period luminosity relationship, which means that we can measure accurate distances to Cepheids using this PL relationship. This makes the Cepheids an important player in the cosmic distance ladder. So you can measure distances to local Cepheids within the galaxy using parallaxes. But since you can also observe Cepheids in other galaxies, you can measure intergalactic distances. And hence, they become crucial calibrators of the cosmic distance ladder. It's impossible to mention about the cosmic distance ladder and not to mention about one of the most pressing questions in astronomy, which is the Hubble's constant tension. So Hubble's constant is the expansion rate of the universe, which is again drawn from the, can be drawn also from the cosmic distance ladder. And what exists currently is an disagreement between the Hubble's constant measured from the late universe, so from the current universe measurements using standard stellar candles like Cepheids, type 1a supernova, and what has been measured cosmologically using the standard cosmological model or the lambda CDM. So to show you a plot on how this is evolving, here you have the H0 or the Hubble's constant measured over the past 25 years. You have the local distance ladder, so which are Cepheids and other standard candles, and then you have the CMB measurements, so the cosmological measurements. And over the years, the precision, the accuracy over these measurements is improving thanks to the improved technology and improved methods. But this also is leading to a bigger and bigger tension between the H0 derived using the early universe or the late universe. This is a 5 sigma tension for the Hubble's constant, which is one of the most important parameters, cosmological parameters. In other way to see it, if you're trying to dig a tunnel or make a bridge from one side of the universe, which is our late type universe, using different standard candles, different methods, so not just Cepheids, but tip of the red giant branch stars, some Myras, and these are all different methods. And if you're digging a tunnel from the early universe, this tunnel or this bridge is not matching. These kind of problems do occur in India, but this is not normal in astronomy, and the Hubble tension is hence one of the pressing issues in astronomy. More tension means more funding, which is where my group in Geneva stands. So we are hipsters, or we were hipsters, because now I'm at KU Leuven. Hipsters standing for measuring Hubble's constant to 1% precision with pulsating stars. Now, if you want to reach to 1% precision with these pulsating stars, you have to understand the pulsating stars much better. So in my case, I was focused on Cepheids, but the other members in the group, they were looking at the other kinds of pulsating stars as well, and other different methods, and other effects as well. So there are other systematics which can affect the application of Cepheids or pulsating stars in the PL relationship, and which is where we were focused at, understanding the systematics which come into play when you want to so accurately use these stars as distance calibrators or to get to 1% precision of the Hubble's constant. So this is my group. Here I am. We are some postdocs and PhDs led by Richard here. And the project I will be now talking more about is VELOCE. VELOCE stands for Velocity of Cepheids, and this is, so in the era of trying to understand Cepheids much better, even when we have a lot of information already about these stars very well, they are very well-studied objects, thanks to the PL relationship, there are still many unknowns about the pulsation physics of these stars, and a lot of other effects which can make them, which can challenge their application in the PL relationship. So this is where VELOCE also comes into, sets in. VELOCE is the first, it's going to be the first data release of high-precision radial velocity time series of Cepheids. This was a project led also by Richard. And the goals of VELOCE were very straightforward, right? So we gathered high-resolution radial velocity time series of Cepheids. And with time series measurements of radial velocities, what can you do? You can do lots of things. First of all, you can look at the RV curve shapes. So as the stars are pulsating, you see this beautiful light curves. This pulsation is also reflected in the radial velocity curves of these stars. So you can also study the radial velocity curves as a complementary information to your light curves. Apart from that, the most important, or one of the primary applications of radial velocity or time series of radial velocities is to detect a stellar companion. Because if you have a spectroscopic binary, it is going to lead to variations in your radial velocity measured over a long timeline, and these variations in radial velocity can allow you to discover these spectroscopic binary companions which are otherwise not visible to you. If you have nice sampling of the whole of the time series measurements, then you could also actually constrain the complete orbit of the system. And then there are other things also you could do using time series spectroscopy, basically understand modulated spectral variability. So these are mainly radial pulsations, but you could also study some other non-radial pulsations and other funky things going on in the atmosphere if you have time series spectra. But high resolution radial velocities and a time series of radial velocities, it comes at a great cost, right? It is expensive, it's a time commitment. And to give you a flavor of why this is still important, you have here an example of, again, of delta Cep, the prototypical classical Cepheid. Here is the RV curve. As I told you, like the light curve, you also have this beautiful RV curve where you can see the whole pulsation of the star within the light curve. Here it is phase folded. And you see these tiny offsets here in the RV curve. So you tend to believe this is just kind of instrumentational error or just some offset in the measurements of the RV, which is not correct. This is actually the spectroscopic companion of this star. So these kind of low amplitude signals from your spectroscopic companion can be detected if you have high precision radial velocity measurements, and which is what sets VELOCE apart from what is now currently available in the literature. To give you an overview of what VELOCE constitutes, you can think of it as a little bit of an all-sky survey in a way, because we cover the northern and the southern hemisphere. The northern hemisphere with our own Mercator telescope at La Palma, and then the southern hemisphere with the Euler telescope, which is a twin telescope basically of Mercator. They are very, very similar. Like even the control rooms are carbon copies of each other. And they both have high resolution spectrographs. So with Hermes at Mercator and Coralie at Euler, we have almost 20,000 observations of almost 260 classical Cepheids, also some misclassified objects. We were able to actually identify these misclassifications thanks to the RV curves. We have a precision of 2 to 50 meters per second on our radial velocity measurements. We have tried to achieve great phase coverage so that we completely sample this pulsation phase of the stars and also the orbital phase wherever we do have orbits or SB1s detected. And the nice advantage of VELOCE that it comes very timely with Gaia. So Gaia radial velocities are, they are measured using a small part of the near-infrared spectrum, while these are all optical RV curves. So this comes as complementary information, and we can also have a nice comparison between the two radial velocity datasets. If you're more of a visual person, then here is an on-sky distribution of the VELOCE targets. In purple, you have all the classical Cepheids, so the 258 classical Cepheids, and the open circles are all the misclassified objects. You can also nicely see the classical Cepheids. They are young stars. They are all kind of centrally located at the galactic disk, which you can see how they crowd the galactic disk here. Next, to give you a taste of the precision on the radial velocity measurements, here you have a plot of the sigma RV, which is the uncertainties on the radial velocities with respect to the Gaia G magnitude. So you also see there is no kind of strong biasing over faint or bright magnitude. We tried to cover the whole magnitude range as faint as we could go with our 1 meter telescopes, 1.2 meter telescopes. And here you see the precision we have tried to achieve with the radial velocities. You can also evidently see that this was made by my Italian colleague. All right, more about the observations. So here you have the number of observations, so the histogram of number of observations for the Cepheids. You see on average we have 30 observations, 30 spectra for star, no, not 30, 50 spectra. For stars, for some best cases, we have more than 100 spectra. We go up to 1,000 spectra for stars. At this point, the color scheme here is not important. What I want to see, what I want you to see is the overall distribution. In terms of the pulsation phase, you can also see there is, again, no kind of biasing towards short or long orbits, not short or long pulsation periods. We try to cover the full range available with great phase sampling as best as we can. All right, let's dig into already comparing VELOCE with all available, not all available, but all with some of the literature data sets. And let's start doing it with Gaia already. What we can see here again with G magnitude and pulsation phase is that, of course, we stop at around 12 magnitude or so because we cannot go fainter than that. So there is a big chunk of Gaia Cepheids which are missing in VELOCE because we don't go fainter than 11, 12 magnitude in G. In terms of pulsation phase, I think we have a good overlap for the whole pulsation phase. But overall, you can see there's a good sample available for comparison because there's a nice overlap between VELOCE and Gaia. So let's already start comparing how the radial velocities look like with Gaia and VELOCE. Here you have on the y-axis, the V gamma literature. Literature in this case is the Gaia DR3 radial velocities minus V gamma VELOCE. So you can think of it as just delta RV, which is the difference between the radial velocities measured with the two different data sets. And this is plotted over time so that we can see if there is any time relation, time dependence of this delta RV. What we can see that there is no time correlation of this delta RV and that there is a huge scatter. There is a difference of up to 3 kilometers per second, basically in the radial velocities measured with Gaia and with VELOCE. This is a problem. This is a time to get worried. So to investigate this further, we try to see if this has any correlation with the stellar parameters, so with the effective temperature, surface gravity, metallicity, and the number of observations here. So again, at the top, you have the delta V gamma, so the delta RV, and the color scheme is not important. The overall patterns tell you that there is no correlation whatsoever with the stellar parameters. In fact, with the number of observations, because Gaia does not have so many epochs of observations as much as we have in VELOCE, you would tend to believe that, okay, with the number of observations in Gaia increasing, we should reach to a better agreement between VELOCE and Gaia, it looks like it is starting to get be the case, but it's not really, because then you have these outliers again with high errors. The problem gets even bigger when you compare amplitudes. So the amplitudes of the RV curves with Gaia and VELOCE, they have a large scatter here, and they have no correlation whatsoever with any stellar parameters, and it doesn't improve with the number of observations increasing. So I don't want to get into the details of who's better, us or Gaia, but what I want you to guys take away is that the measurement, the method of measurement of the RVs is very crucial. And there is a difference between how the radial velocities were measured between Gaia and in VELOCE, which leads to these kind of discrepancies. So whenever you're using or you're planning to combine your own radial velocity measurements from Hermes or from wherever instrument with some other literature data sets, you have to be careful with what method was used to derive those radial velocities, because these differences can be due to instrumentational differences or in methods in reducing or deriving these radial velocities, and the measurement of the RV can be significantly different because of that. So you might see large offsets in your radial velocities and would be misled into thinking this is a binarity sign or something, while this could be just some instrumentational differences. This is where also the next part of my slide comes into play. So since VELOCE has this long baseline, right, with Coralie, this is again still Coralie, but just an upgraded version, and Hermes, we were very curious to find out the stability of these instruments over this long or the full baseline of VELOCE. And you see that we have quite good stability with Hermes and with Coralie over the full baseline of VELOCE. Using this stability of VELOCE, you can actually compare the stability or non-stability of the other literature data sets. So we checked the RV data from other data sets and found the 0-point offset corrections, basically. So the offsets we can have with VELOCE and with the other RV data sets. So you have the same star measurements from VELOCE and not from VELOCE, and you can measure an offset. Now, these 0-point offsets could be because of many reasons, right? Again, as I mentioned, can be instrumentational differences, can be differences due to the RV measurement, the methods in RV measurements. So these differences could be due to different reasons, but the 0-point offsets, they allow you to meaningfully combine them with your data set and then to look for long-term effects or variations or whatever in the radial velocity time series. So as part of the VELOCE DR1, we will be giving out these 0-point offset corrections for 30 literature RV datasets. This includes offsets for Coralie, Hermes, even if they are very tiny, as well as for other literature datasets, as well as for Gaia, which means then you can combine the Gaia RVs as well with other, with our baseline as well to extend your radial velocity time series. So if you have stayed with me so far, continue to, because now gets the most exciting part of this talk. This was the project led by me. So this was the part of single line spectroscopic binaries. So of course, when you have time series radial velocities, you want to look for binaries within your stars, within your sample, right? But why are binaries in Cepheids even more important, or it's important to know about them? Because it's important to understand if the binarity can have any effect on the PL relationship itself, right? So you have a companion, the light from companion can affect the observed brightness of your Cepheid, then it can impact the intrinsic brightness. It can also have an impact on the pulsation characteristics. There can be some interactions. So depending on the type of your of the binary companion, as well as the configuration of the system, it might have an effect or not at on the PL relationship. So it's very important to study this. Apart from that, it's also important to know how much we should be worried about this. So are Cepheids in binaries a rare thing or a very common thing, and how much they affect it, and how much should be worried about it? Also for local distances, so using parallaxes for the Milky Way Cepheids, the binarity can have an impact, or an orbital motion can have an impact depending on a resolved or unresolved companion. So binarity can have a lot of effect on the Cepheid physics, and to understand that, it's important to also detect these systems. Now, how is this traditionally done? I already mentioned this a bit. You're looking for radial velocity trends, basically. So you're looking for variations in your mean radial velocity over a long baseline, because your spectroscopic companion, your binary companion, will lead to this line of sight radial velocities that you're measuring. And if you combine this for the year is a baseline of 25 years for DelCep and WGEM, and here they have combined measurements from actually different literature data sets and comparing it with the mean RV. If you see these kinds of large variations, it's a hint that this guy is a spectroscopic binary. The advantage we have with VELOCE is that we have our own time series measurements, right? So even without combining any other literature data sets, you can see these repeated patterns in the RV curve. So the different colors in this RV curve are different epochs. So each color, you can think of one pulsation phase, basically. And you can see this radial velocity, the whole curve being shifted depending on the amplitude of your spectroscopic companion. If you now see the bottom panel of this, these are the residuals, basically, of the top panel. And in fact, here you see the different epochs completely also, again, being shifted, which is another hint for you that this is a spectroscopic binary. So looking for variations in the mean V gamma, we detected 76 SB1s, or 76 spectroscopic, single-line spectroscopic binaries amongst the 258 classical Cepheids from VELOCE. So this leads to an SB1 fraction of 30% within VELOCE, and this is the on-sky distribution. And I have color-coded this with the Gaia G magnitude to show you that there is, again, no biasing towards fainter or brighter magnitude. In fact, we have quite many stars with faint magnitude, and to get the time series radial velocities of these guys, to be able to detect their binarity and to also have their orbits is a big time commitment and an expensive time commitment. So VELOCE constitutes of the VELOCE SB1s these are 76 SB1s. For some of them, we do have orbits as well, and they are distributed over the whole Gaia GMAC range. All right, so now you have detected your SB1s. You want to further make more use of these radial velocities you have, right? So if you have a good enough sampling, good enough time series measurements, you also want to get the orbit of your systems. So this process is usually done by Keplerian fitting. So you just fit the Keplerian equation to get your orbital parameters with your RVs. However, with the Cepheids, you have to be a bit careful because you also need to fit the pulsation, because the radial velocity curve also has the information on the pulsation of the star. So we went we did this by combining the Fourier series, so Fourier fitting for the pulsation curve, and the Keplerian fitting, so a combinational fit of Fourier plus Keplerian. So here you have the pulsation curve fitted with a Fourier series of certain order of terms depending on how complicated your pulsation curve is. And here is the beautiful orbit of del Ceph, so the orbital motion fitted with the Keplerian fitting. This is, of course, possible when you do have a good phase coverage, when you do have the orbit completely sampled, then you can constrain this orbital elements very well. What do you do when you don't have a good enough sampling? So when you see differences in the mean, you see variations in the mean V gamma, but you cannot constrain the orbit yet. What we did in that case is we fitted the Fourier with a polynomial fitting just to kind of quantify the amplitude variations we see, to quantify the amplitude of the, or the semi-amplitude of the spectroscopic companion and the timeline for these variations. And then it is possible, right, that we don't see any mean V gamma variations in our baseline, because our baseline is just 11 years. But the star could still be an SB1. Maybe we don't have enough sampling, we don't have enough data, or the orbit is much longer than our baseline. So in that case, we also combine the literature data sets meaningfully now by using the 0-point offset corrections I introduced to you all. And doing this, we not only detected some SB1 systems, but we were also able to fit really long orbits. So here in this picture, you have an example of AW per. VELOCE data is only here because that's the timeline, that's the baseline we covered, while we have the 0-point offset corrected other literature data sets nicely fitting, helping us fit this beautiful long orbit of 40 years of AW per. So we were also able to then fit orbits much longer than our baseline of 11 years. So we have a full orbital period range covered here as full as possible. Let's already start looking at how the results look like. So here is the, I wanted to show an example of some orbital elements, and I have chosen the eccentricity versus orbital period, the very famous ELOC-P diagram, basically. Here you see how these are distributed. And I promise to you that this will be the most populated ELOC-P diagram of Cepheids you'll find, because this is the most complete and up-to-date data set that is available currently. To make this diagram even more interesting, let's compare it with population synthesis models. So here I have plotted or overplotted my observations, the observed eccentricity and orbital period, with population synthesis model from Nielsen et al. And there are several things going on, so let's go step by step. First, from the population synthesis, you have this yellow zone here. So yellow to dark is basically the probability of finding these systems. Yellow meaning that you have a very high probability. Somehow, the population synthesis model expect a very densely, like a very crowded zone, yellow zone here, which is not what we find from our observations. From the observations, it's a big spread in the whole range. Next, sadly the observations don't go, sadly the models don't go beyond 10 years, but we have some orbits here as well, so it's a bit difficult to do this comparison. But you have this blue zone here, where you don't expect a lot of systems, or not a lot of systems are predicted, but you still have them with the observations. Another thing which I like to point out, if you were to extrapolate this yellow zone, you definitely predict these systems, and you would think, yeah, these systems are predicted or expected to be there. But I do want to highlight that it is very difficult to find these systems. It's because high eccentricity at high orbital period requires very strict monitoring, time series monitoring of these stars, because the eccentricity drops by quickly. And if you want to really constrain this kind of high eccentric orbits very well, especially for long orbital periods, then you have to have a good follow-up with your radial velocity measurements. Another interesting thing which we discovered was this guy here. So this star here is at the border of where SB1 Cepheids are expected. This guy, or his name is our crew. Our crew is an SB1 with an almost circular orbit. Here I have shown an orbit with VELOCE as well as some literature data set, and with both, like combining VELOCE with literature or without literature, both ways we find an orbit close to 237 days, so much smaller than a year's orbit. A year is usually, or 365 days is usually the lower limit of orbit expected for Cepheids, because these are like these giant stars. But we found our crew, which means that such short orbit systems also do exist. Of course, we don't know at the moment how many of them, but I would like to introduce you all to our crew, who is the shortest known orbit for an SB1 Cepheid to date. All right. Let's compare now a bit with the Gaia astrometry flags, right? So Gaia provides several of these astrometry flags. So this RUVE here, the astrometric axis noise, these quality flags are supposed to help us to know if we should be using the parallaxes or not, basically. They tell you the quality of the parallax itself. The quality flags, the astrometry flags, they can have different information. So they can be affected due to the binarity. Your parallax could be affected due to binarity or some other kinds of effects. But it is all put together in this quantity called RUVE, for example. And Gaia proposes a threshold of 1.4 in case if you want to filter out your binary systems, for example, from your sample. So here I've plotted the SB1 and non-SB1 distribution of this RUVE parameter. What you usually see is that, in general, the RUVE of the SB1s is higher, actually. So the binaries do have a higher RUVE than the non-SB1s. But you still also have some non-SB1s here, which have much higher RUVE than 1.4. And these guys, this is basically telling us that there is more information in the RUVE than just binarity for the Cepheids. So the RUVE is not only affected by binarity, but something even more. And it is also telling us that the filter of 1.4 is not a great filter, because you still have SB1 systems below this 1.4 filter. So the Gaia RUVE of 1.4 is not a great idea if you want to filter out your SB1 or binary Cepheids. We were also curious to investigate if the RUVE has any connection or correlation with the orbital parameters or orbital elements. So here I have plotted the A sin I and the orbital period with respect to the RUVE. If you completely ignore this corner point, then you see this large scatter in the whole RUVE range. Again, there are stars much with smaller than 1.4 RUVE as well. So we also did not detect any correlation between the Gaia RUVE parameter and the orbital elements of our systems. And the takeaway message that I want you to have from here is that the SB1 systems, if you want to filter them out from your sample, especially for Cepheids or pulsating stars, then RUVE of 1.4 is not a great filter. All right, now you might be curious if there are other kinds of binaries within VELOCE as well, right? Because we discussed about the SB1 systems. So there are also some double-line spectroscopic binaries, so basically eclipsing binaries. We have 7 systems, but they are all non-classical Cepheids, so other kinds of Cepheids. and within VELOCE, 7 of them. Then we have some visual binaries. These were detected using the guiding camera images of Hermes and Coralie. So we have 17 such systems. Then we have a visual plus SB1 systems. These are the most interesting ones, my favorite ones. Here you have an example of this. So FOCAR is an SB1, is a spectroscopic binary. And then you have this visual companion here, which is nicely visible in the guiding camera image of Coralie. So this star actually could be a triple system because it has a visual companion as well as a SB1. The physical relation of the visual companions we have detected in the guiding camera images is still to be done, is still under process. But if they are all related, then we have almost, I think, 15 or 17 triple systems within VELOCE. So these are stars with visual companion plus a spectroscopic companion. All right, let's now get a complete overview of the VELOCE SB1s. So basically, these are in orange are the new VELOCE systems. So here are the new detections, which we have 32. So 50% of the sample is completely new detections, which were not known to be SB1s previously. And then these are the orbits, new orbits here in orange. And you see that for fainter magnitudes, we increase by a factor of 2 almost the number of known orbits in fainter magnitudes now with VELOCE. You also see in general that, yeah, we have a good overlap with what also was known previously in the literature. So a comparison of the orbital fits and quality of the orbits can also be done because we also have some sample which was in common with the previous literature study. So we have a sample of 76 Cepheids. I already mentioned 32 of which are completely new detections, and we have orbits for 50% of them. And we also detected several interesting targets. One of them I gave an example of, that's our crew. And then, of course, we did some analysis and comparisons with Gaia itself as well, and found out that Gaia RV of 1.4 is not a great filter. All of this will soon be out. It is under review for publication in ANA and will be soon out on archive or whatever, but we can always discuss about it if you have more questions. To give you a bit of an overview of what VELOCE data release will constitute of, so this will be data release of radial velocities, not spectra, but the spectra can also be obtained if you are interested. You can contact us. So this will be the first data release will constitute of measurements until 2022, so an 11 years baseline. We will provide the radial velocity time series and the uncertainties on those. We will also provide the Fourier parameters, so basically the pulsation model and the uncertainties on the pulsation model. And then for the spectroscopic binaries, we will also provide the orbital fittings and the orbits and other parameters related to the orbit. Apart from that, also there will be refined pulsation periods. So these pulsation periods are completely derived using the radial velocity curve. So again, complementary information to your light curves. Then we will provide also the 0-point corrections from Hermes, Coralie, and other literature data sets, which can also be useful if you're interested in radial velocity analysis. And with that, I thank you all for your attention. So this is me at both the sites in La Palma and La Silla, enjoying my time there during this project and the opportunity that I got to observe at these places. And if you have any questions, I'm ready to take them.
Thank you, Shreeya, for a really interesting talk. Are there any questions?
In your Italian pizza or your Italian flag plot,
Yes.
did I see a systematic difference between Hermes and Coralie?
Yes, that is true.
And
Why?
now that you're living on this side of the border, who is right?
I like both the instruments equally. Huh? No, there is a difference between how the uncertainties, the radial velocity uncertainties are measured with Hermes and Coralie in the pipeline. So with Coralie, they are using the photon noise as the main dominant source in Hermes, it's done with the covariance metrics, I think, of the Gaussian that is fitted to the CCF. Now, this leads to overestimation of RV uncertainty for brighter stars, for example. So this is the reason why you have this systematic high uncertainty. It's probably overestimated in the pipeline.
Okay, so it was the uncertainty. It was not. It was the absolute.
No, it's not the actual representation of the measurement uncertainty in a way. It's
the uncertainty,
radial velocity uncertainty. Yeah.
And
this has been just last point. For example, for Delta Cep, which is an equatorial star which was studied using Coralie and Hermes both, they kind of also investigated, actually, there's a dedicated paper to this where they investigated this effect on why I'm saying that this is overestimated within Hermes.
And the Gaia RV discrepancy, isn't Gaia RVs anyway terribly bad at magnitude 12, like more than a kilometer per second uncertainty?
Could be. Well,
I thought so. Well,
we tried to use the most reliable time series that, I mean, there were some filtering done. So yeah, maybe for the fainter magnitudes, we didn't include them in the comparison. But overall, the scatter that you saw, the delta RV between VELOCE and Gaia is magnitude independent. It is there existing for brighter and faint stars, both.
On the Gaia comparison, because Gaia only measures in the near-infrared,
yes,
which is maybe also atmospheric, no? Because those lines are, I don't know, what is the most, the strongest opacity source is H minus or? I mean, so within the whole atmosphere, the near-infrared is formed, or those lines are formed at a certain position in the atmosphere.
Yeah, indeed.
Which is different than if you use the whole optical spectrum. And did you test that? Did you?
So this is something we are on to now. Like we have now discovered the difference between them, and there could be several reasons you could attribute it to. So of course, this is a known effect that the radial velocity measurements, even optical to infrared for the same star, can differ, and because of the different lines you use or the masks is another issue. If you also the change of mask that you use for your template fitting and so on. So of course, this can be one of the things. The other thing is that in Gaia, the template used, so the for your CCF, is varying with the whole pulsation phase, because with the pulsation phase, the temperature is varying, right? So they are using, basically they are using each spectra as a separate star in a way, and they have their own routine which looks for the appropriate temperature and whatever, and then they use this special, this CCF, this template for the CCF. So this is another thing, like one thing interesting would be to use our method. We don't have the Gaia spectra, so, but use their method from A to Z on our spectra, and to see if we then get the Gaia radial velocities, and then we can know if this is an effect of the processing or of the spectral lines that are used, or the reason being that part of the spectra used and not a complete total spectra used. But this is not completely known.
But for Hermes, the reddest spectral orders are not very well wavelength calibrated.
Exactly,
so
yeah. So we'll have to see how to do this.
Hi, thanks for the nice talk. I was wondering, you were talking about the 0-point offsets between other data sets, and so you showed the data set which covered in total then, well, 40 years ago or something. And I was wondering how you would do the 0-point offset there, because you showed it's a binary, so you can't assume that it's at the same kind of,
Great observation, great question. We didn't use the binaries for the 0-point offsets. So we first identified our binaries amongst these 260 stars. We know that there are 76 binaries or whatever. And not just these binaries, but also some stars, which show some non-radial pulsations or some things which we cannot characterize completely within the RV curve. These stars were not used for the 0-point offset measurements. Only stable stars who had a stable RV over this long baseline of VELOCE itself were used then to measure the 0-point offsets with the literature datasets. Because you're right, if we would use binarity, then these could be just offsets because of binarity and not because of an actual difference. Yeah.
But so the dataset, the 2-3 other datasets that you used covered more stars than just I'm just talking about the plot with the long period binary, right? Because you needed the 40 years.
Yes. Yeah.
So the longest to go contained more stars.
No, not
as
all
well,
data sets have all stars overlapping with us. So the number of stars used for the 0-point offset correction, it varies from data set to data set because it doesn't overlap. So we have comparison with 30 literature data sets, I said, right? And each one, there are some data sets which are bigger. I think we have the most largest overlap actually with Gaia, if we treat Gaia as a literature data set. But I think it's mostly with Gaia and then some other already existing data sets as well. But the number of stars used is different. And so we are not just providing the 0-point offset, but also an error on the 0-point offset as well. And this error constitutes or represents the number of stars being used, because of course, if the number of stars were too few, your 0-point offset might be a bit inaccurate.
Okay, thanks.
In a sense, Shreeya, you answered my question now. So I was seeing the 4 km per second scatter, and then I saw the binaries, which are about 4 km per second. So I think I was naive in assuming that these were related, but indeed, it seems that they are.
We tried to filter out the binaries in this analysis to our best knowledge. But of course, there could be stars which are not yet long orbits which are not yet detected as SB1s or something. That is very much possible. But we tried to filter them out, at least in the analysis.
Yes.
Hey, I'm curious about your period eccentricity diagram compared against the theory. So what actually from the theory side produces that dependency?
I have no clue, actually.
Okay.
I am not a theory expert. I don't know if I can quickly go back there to the plot here. I have no clue. These dependencies on or this expectation, or maybe it is explained better in the paper. I cannot think of it in top of my head on why you have this expected, but it is basically the configuration of the system, assuming a distribution for the mass range and everything, right, for your binary system. So all that goes into such kind of population synthesis models, I guess, leads to these kind of distributions. I don't know the details of it, Yeah, I would have guessed this is mostly the top is more or less from interacting binaries, and then you would just be sampling essentially the orbital distribution of stars before interaction. Yes, But then the eccentricity would be a thermal distribution, and so so it confuses me a bit. No, I cannot give you the details of why this zone, but and there is also, sadly, nothing more recent available. So this is 2015, okay? It's not that far behind in time. But apart from that, there is no recent dedicated Cepheid binary population synthesis models available, which can tell you which can update this picture. Okay, thanks. Welcome.
Thanks for a very interesting talk. So you have this new set of refined pulsation periods.
Yes.
I'm wondering to what extent these are affecting the period luminosity relation, the Leavitt law. Do you expect a big change?
We actually investigated it. So the data release paper, we wanted to stick to as much only data description as possible. But of course, we were very curious and also wanted to investigate the science and the physics that we also discovered, right? So yes, there are these refined pulsation periods. We compared them also with the pulsation periods from the light curves, and to find out how different they could be. Also tried to understand its effect on the PL relationship. For now, this refinement is really at a very small level, at a really small effect. So what I would say is that the bigger effects to your PL relationship would not be the pulsation period itself, the refinement in pulsation period, but effects due to metallicity, effects due to binarity, effects due to crowding if you're looking at Cepheids in clusters. So these guys could have more larger effect on the PL relationship than the pulsation period itself, because for now we have such good time series, radial velocities, as well as light curves for these guys, that the pulsation period is really very well refined or defined. What happened is, with this long time series, we also could find some nonlinear trends in the pulsation period, or some period changes, over a long period, if I could make that more complicated. So that is also what we found out, but the effect is very small on the PL relationship itself.
Are there any other questions? If not, I think we can thank Shreeya again for the talk. Thank you for coming.